Welcome everybody to my presentation of the new features for the digital design of foams, composites and ceramics in Geodict 2021. My name is Martina Humbert, and first I would like to introduce myself. I studied mechanical engineering at the University of Kaiserslautern. I also did my PhD in Kaiserslautern at the Institute for Composite Materials. And in 2019 I joined Math2Market as business manager for foams, composites, ceramics and metals. In contrast to some of the sessions of my colleagues, which have very specific titles such as filtration, this session is just called Digital Material R&D. So first of all, I would like to give you an overview of the topics which we assign to Digital Material R&D. And one of these is the prediction of mechanical properties of materials such as composite laminates. Here you can see the fuselage of an aircraft and also a generated microstructure of such a laminate, and you can use Geodict to predict the stiffness tensor of such a material. Moreover, properties which are important for manufacturing can be determined, such as the permeability of a textile. This property is needed to design resin infusion processes which are used in serial production of composite components as this car body. When it comes to porous materials, for example foams or structures made by additive manufacturing, Geodict is an excellent tool to analyze their characteristics, such as pore sizes or percolation path. Another key feature of Geodict for digital material design is the simulation of large deformations. Especially the compression of foams, whose digital models include all components such as struts and faces, is a unique capability. In many materials, not only mechanical but also physical properties are important. Take ceramic matrix composites, as they are used in brake discs or heat shields. Besides excellent mechanical properties, they also need a specific thermal conductivity, which can be simulated in Geodict as well. And of course, none of these simulations would be possible without the import of a CT scan and Geodict structure generators. With modules like FoamGeo or FiberGeo, realistic voxel-based structures can be generated with a few clicks and then used as geometry for simulations. And thanks to Geodict's voxel approach, no meshing is needed in the entire workflow. The generation of realistic structures, in this case composites, also includes the first new feature I'm going to talk about. After that, I will show you our improved material database, the fast prediction of stiffness sensors, and the tremendous runtime reduction of the simulation of large deformations. For the simulation of composites, it is important to include imperfections into the model, because they have a large influence on mechanical or physical properties. Waviness, for example, reduces the stiffness because the fibers are not perfectly aligned to the load direction. An inhomogeneous fiber distribution can open unwanted flow channels for the resin and foster race tracking during resin infusion. And that are only two examples for the effects of imperfections. Still, they are often omitted because it is not easy to generate an imperfect model, especially in standard finite element simulation. This is a lot easier in Geodict, as you can see in those pictures. On the right is an image of a binder tape, and you can see significant waviness. This waviness can be remodeled in FiberGeo using curved fibers, and its influence on stiffness and permeability can be simulated. Other common problems are resin pockets and inhomogeneous fiber distributions. They can lead to uneven stress distributions, and you can also remodel them in Geodict with the help of Gaussian random fields, as you can see on the microstructure and the Geodict structure. And I would like to point out that the Geodict structure is not imported from a CT scan. It was reconstructed in FiberGeo based on a micrograph and a datasheet. In Geodict 2021, the modeling of misalignment is a lot more convenient thanks to a new orientation setting in FiberGeo. Now you can define an angle around the main direction. And this angle is not limited to a certain value, but can also follow a distribution, such as the Gaussian distribution. On the right, you can see the difference between the standard orientation setting on top, with which all fibers are perfectly aligned, and a structure generated with angle around direction at the bottom, which looks now even more realistic. Next, I'm going to show you our improved material database. For micromechanical simulations, material laws are crucial, and the example of a fiber-reinforced plastic shows the complexity of this topic. When you look at a part as this engine carrier manufactured by injection molding, you can see that its material consists of two main components, the fibers and the polymer. And they differ fundamentally in their mechanical behavior. The fibers deform almost linear elastically with a sudden brittle failure. Their material law is defined by Young's modulus and tensile strength, which you can often find on datasheets. The polymer, on the other hand, shows a ductile, elastoplastic or viscoplastic deformation, which is defined by more complex material laws. They are often not included in datasheets. In GEODIC 2021, we tackle this problem in two ways. First, we expand our material database by including more and more materials which you can use. Second, we facilitate the definition of your own material laws. In this screenshot, you can see that GEODIC 2021 comes with a selection of different carbon, glass and aramide fibers. In addition, you can define your own fibers using GEODIC's failure law for brittle materials. You just need a Young's modulus and a tensile strength, and it also supports transversal isotropic materials. That makes it perfect for carbon fibers. GEODIC now also includes a wide range of polymers, and many of them already come with a law for plasticity. If you want to define your own law for a polymer, you can choose from our redesigned user interface between laws for elastoplasticity, viscoplasticity, and damage. For elastoplasticity, perfect plasticity, bilinear hardening, and exponential hardening are available. For viscoplasticity, you can choose between a linear and a nonlinear Purcina model or a model after Michelin-Suquet. For damage, exponential is available. Of course, you can combine the different models. And moreover, you can transfer a tensile test into a material law with a fitting function. The fitting function is very handy if you have a material in your microstructure of which you can make a tensile test. For example, a fiber-reinforced epoxy resin. In this case, you can make samples of the pure epoxy resin and put them in a tensile testing machine. From this test, you get a stress-strain curve that consists of a table of stress-strain pairs. This table you can copy into GEODIC's material database under measurement. Then you can fit the parameters of a chosen plasticity or damage law to this curve. Fitting is available for perfect plasticity, bilinear and exponential hardening, and damage. This law you can then use for simulations, for example to study the influence of fiber direction or fiber volume content, or also later on with a different fiber type. You can also look into the details of deformation, such as the plastic deformation in the polymer. This is information you would never get from a tensile test because it simply cannot be measured. So when you have your material law, you can move on to mechanical simulations. And the first step is the prediction of the stiffness tensor. Composites, ceramics, metals, and sometimes also foams are used in mechanically loaded components. Applications include automotive, aerospace, shipbuilding, energy industry, and many more. And to choose the right material in the right place, it is important to know its stiffness tensor. Of course, you could do that by tensile tests, which even don't take that long. But the more complex your material, the more time-consuming is the manufacturing of the material sample itself. But these complex materials are the ones that offer outstanding properties, let it be lightweight, high stiffness, or low thermal expansion. In GEODIC, you can digitally model these materials and then fastly predict the stiffness tensor using Elastodic's FEMATHWOX. To predict the stiffness tensor, a linear elastic tensile test is simulated in GEODIC. This simulation is already quite quick by nature, but when it comes to large structures, such as this reef, runtime and memory consumption can be high. To still offer you a quick prediction of the stiffness tensor, we give the option to choose downsampling. Downsampling means that 4 by 4 by 4 voxels are combined into one voxel. That reduces the number of voxels and thereby runtime and memory consumption significantly. And downsampling has a big advantage over just decreasing resolution of your model. The material law in a downsampled voxel is a combination of the material laws of the original voxels. So both materials are considered during simulation, whereas in a coarser model, each voxel has only one material law and information is lost. To demonstrate the speed up due to downsampling, I will show the example of a weave. In this weave, every single fiber is resolved, and that leads to a large structure with round about 5.5 billion voxels. On this structure, we compute 6 load cases, namely tensile load in x, y, and z direction, and shear load in yz, xz, and xy direction. In this example of the weave, the runtime could be reduced by 97% when downsampling is activated. Also, the required memory was reduced by 97%. It went from 1 terabyte to 30 gigabyte. That also means that you need a large simulation computer without downsampling, but with downsampling you can run the simulation on a workstation. This huge speedup was achieved while the difference of Young's modulus in x direction was only 1%. You can also see in this diagram that the speedup with an increasing number of processes is very good. In GEODIC 2021, downsampling is available for all types of mechanical simulations. The next step after the prediction of the stiffness tensor is the simulation of large deformations. And in GEODIC 2021, this will be much faster. The simulation of large deformations can give you new insights into the microstructure of your material. On this bead of a particle foam, you can see how each cell deforms due to the compression of the bead. The cell walls start to bend and buckle, and then the cells collapse. It would require a lot of very expensive equipment and time in the lab to get this much information from an experiment. Simulation of large deformation also offers the opportunity to analyze plasticity, damage, and failure. In this video of a digital tensile test on a short fiber reinforced polymer, you can see that the plastic strain starts around the fibers where the stress peaks are highest because of the large stiffness contrast between polymer and fibers. But these simulations require long runtimes, or let's say they did require long runtimes, until the release of GEODIC 2021. But how is this runtime reduction achieved? When you look at the log of a large deformation simulation, you can observe that writing on the disk is the bottleneck. And writing the deformation files is responsible for that because it takes particularly long. So for GEODIC 2021, our colleagues from Fraunhofer ITWM, who developed the FieldMath solver, have implemented that those deformation files are kept in memory during the simulation, and that reduces the runtime significantly. I will show you an example of a foam structure with 500 by 500 by 500 voxels. We computed a compression in z direction of 80% in 40 steps. We compared runtimes and memory consumption with and without keeping the deformed geometry in memory. Moreover, we looked at an additional speed up by also using downsampling. So let's have a look at the results. All reductions I will mention now are compared to the first column, no downsampling and simulation on the hard drive. For elastic materials, using downsampling reduces the runtime by 20%. You can see that from here to there. Keeping the deformed geometry in memory reduces the runtime by 67% from here to there. A combination of downsampling and keeping the deformed geometry in memory leads to a reduction of 92%, so from here to there. For plastic materials, the runtime is longer in general, but the effect of our speedup measures is higher. Using downsampling reduces the runtime by 30% from here to there, keeping the deformed geometry in memory by 77%, and the combination of both leads to a reduction of 95%. So from this first column to the last. Concerning the memory, the image is a little bit more heterogeneous. By using downsampling, the memory consumption can be reduced by 80% for elastic materials, so from here to there, and 92% for plastic materials respectively, so this column compared to this column. Keeping the deformed geometry in memory, though, increases the memory consumption by more than 70%, so those two columns compared to those two columns, and you can see that the memory goes up. Using downsampling reduces the memory consumption again by 56% for elastic and 79% for plastic materials, compared to no downsampling and writing on the disk. So again, those two columns now compared to those two columns. So you can see that keeping the deformed geometry in memory is a trade-off between runtime and memory consumption. If you do not have enough memory, you can still write on the disk. But we think the runtime reduction is worth the extra memory. When you use a method like downsampling, you will have to look at the stress-strain curves to see if they differ from simulations without downsampling. And you also might want to check that keeping the files in memory does not affect the results. In this diagram, you can see the stress-strain curves of all four combinations. The curves, whose only difference is whether the fields were written on the disk or kept in memory, are identical. So you can see only one of them. You can also see that until 60%, the curves with and without downsampling match quite well. They are almost identical at the beginning. That means that both structures have the same stiffness. Also, the onset and early evolution of plastic deformation between 2 and 10% are identical. Then both curves show a slight decrease in stiffness, caused by the buckling of cell walls and collapsing of cells. But the stiffness of the downsampled structure remains at a higher level than the stiffness of the original structure because its cell walls start to get into contact earlier, as the edges of the voxels are smoothed when downsampling is used. This effect is also responsible for the earlier onset, at around 60%, of the steep increase in stiffness of the downsampled structure when the foam is compressed almost entirely and the stiffness approaches bulk stiffness. And although the curves diverge at high compressions, keep in mind that the runtime was reduced by 95%. Finally, we will have a look at the compression of the foam. In this example, no downsampling was used. You can see that after a linear elastic increase, the cell walls start to bend and buckle. That leads to a lower stiffness as the cells lose their stability. Then the cells start to collapse, and as soon as a certain amount of cells is crushed, the stresses increase rapidly. And with this video, I would like to end my presentation. I would like to thank my colleagues who developed these new features and contributed, for example with simulations, to this presentation. And of course I would like to thank you for your attention. If you have any questions, please feel free to ask. I'm happy to answer.